How does a falling ball move after it is dropped? This question asks for a careful analysis of the ball's velocity and position as it falls. In a nutshell, the ball's velocity increases steadily in the downward direction, but its position shifts downward further with each passing second. Now, to help you understand these positions and velocities, let me suppose initially that gravity has vanished, and let's look and see what happens to a falling ball in the absence of gravity. In a live class, I can make that supposition, but only in my head. In video, I can show you that possibility. Now, this is a class about how the real world works. It's a science class. It's not about science fiction. So whenever I do this sort of thing, when I show you how things would happen if I change the rules slightly, I'll let you know. So, off goes gravity. Let's see what happens to a ball that's released from rest in the absence of gravity. Gravity has been switched off. Now, the acceleration due to gravity is 0. And let's see what happens when we drop a ball from rest. Ready, get set, go. There's no acceleration due to gravity, so the ball's velocity starts at 0, which is when I release it, and it stays at 0. The ball's inertial, and it does nothing. It just remains there in space. Gravity is still switched off, and I'm going to drop the ball from rest again. But this time, I'm going to plot the ball's velocity versus time. Now, velocity is a vector quantity, and plotting a vector quantity is difficult. After all, it has an amount and a direction. So what I'm actually going to plot is the vertical component of the ball's velocity. That is, the portion of the ball's velocity that lies along the vertical direction, and therefore that affects the ball's altitude, or height above the ground. So if it's moving downward, that contributes a downward component of velocity. If it's moving upward, that is an upward component of velocity. Ready? Again, no gravity. Here we go. Ready, get set. There you have it. The ball's velocity starts at 0, and as time passes, the velocity stays at 0. It's inertial. The acceleration due to gravity is 0 in the absence of gravity, and so the ball's velocity is constant. Well, this is getting tedious. We need some action. Gravity's still switched off, though. So if we want some action, we want some motion, I've got to do it myself. So I'm going to drop the ball again, but this time I'm going to give it a push before I let go of it. I'm going to make sure that it has a downward velocity from the moment that I let go. What it does with that velocity is up to it, but I'm going to give it that starting velocity in the downward direction. And as it moves, I'm going to plot two things. First, I'm going to plot the vertical component of the ball's velocity, as before, but I'm also going to plot the vertical component of the ball's position. What's the vertical component of position? Well, it's the altitude of the ball relative to some starting point, some 0. And I'm going to make the 0 the point at which I let go of the ball. So if the ball moves downward relative to the point where I let go of it, that's downward, a position that's down below where it started. Those will be the negative values for my vertical component of position graph. If it moves upward, which it won't this time, those would be the positive values of my vertical component of position graph. So here we go. I'm going to release the ball, not from rest, but with an initial downward component to its velocity. And we'll watch the ball fall in this gravity-free environment. Are you ready? Get set, go. It was inertial. The ball coasted downward. After all, it has zero net force acting on it here in the world of no gravity. And so whatever velocity it started with, it retained. So as time passed, the velocity didn't change. The position of the ball did change, however. The ball used its velocity to cover some distance. And with each passing second, it went lower and lower and lower and lower until finally it drifted out of view. Without gravity, the ball becomes inertial after you let go of it. It's experiencing no external forces, and so it travels at constant velocity in accordance with Newton's first law of motion. Whichever way it was heading when you let go, it'll keep heading in that direction, and there's nothing special about downward anymore. Finally, it's time for some gravity, but just a little. If I turn on the full Earth gravity, the ball drops so fast that I can't show you what's going on. So I'm going to start with just a little bit of gravity, 1/100th of the full Earth gravity. That means that the acceleration due to gravity here in my special video world is going to be 0.098 meters per second. That's 1/100th of the real world value. What you'll see then is the ball accelerate downward. It'll go faster and faster as time passes. And at the same time, its position will change. It will cover distance in the downward direction. I'm going to drop it from rest, make things simple, and you'll watch it accelerate downward and travel downward in response to a very weak version of gravity. Are you ready? Here we go. Ready, get set, go. How about that? It started very slowly. In fact, for the moment I let go of it, it was at rest. And then it went faster and faster and faster as time passed. And it used that downward velocity to travel more and more with each passing second. So in the first second, it didn't go very far because it was traveling very slowly on average. The second second, it traveled farther. The third second, farther still. And by the time 5 seconds had passed, it had pretty much drifted out of view. So that's life with weak gravity. To show you full gravity, the whole Earth's gravity, to return to the real world, I need more height. I can't work in this little laboratory. We got to go use the entire physics building at the University of Virginia. And that's what we're going to do. The Earth's gravity is strong enough to make things happen fast. And that's why I need more height to work with. I'm going to drop this bowling ball out of the 3rd floor window of the physics building and let the ball fall all the way past the basement. But even with that amount of height to work with, the fall is going to be over in a little more than 1.2 seconds. So we'll do it initially at full speed, and then because this is video, I'll slow down the video and begin to mark it up so that you can see how a falling ball moves. Going down. Here's a bowling ball. Ready, set, go. I told you that fall would be quick. It's hard to even see the bowling ball as it plummets. To make it easier for you to follow the bowling ball during its descent, I'm going to highlight it with a red dot. So here is the same fall, but with a red dot marking the position of the bowling ball as it falls. Ready, set, go. Because I'm trying to explain how a falling ball moves after it is dropped, I need to be able to show you how the ball's position and its velocity change with time. But recall that while it takes only a single glimpse to observe the ball's position, it takes 2 glimpses to determine the ball's velocity. And if you go as far as looking for acceleration, it takes 3 glimpses. It would be helpful, therefore, if we had more than one glimpse of the ball's position visible simultaneously. Since this is video, I can do that. The camera records 30 frames per second. That's 30 glimpses of the ball's position every second. What I can do is cause the whole video to remember all the previous glimpses of the ball up until the current moment. That means that every 30th of a second we'll have a glimpse of the ball. So here's that same falling bowling ball marked by a red dot, and all the previous red dots will linger on the screen so you can see the evolution of the ball's position, and from that take a look at its velocity and acceleration. Ready, set, go! That trail of red dots tells us a great deal about the bowling ball's movement after I dropped it. At first, the bowling ball was moving downward very slowly, and it remained close to my hands. It had a small downward velocity, so its position was shifting downward slowly. But that slow descent didn't last. After about a second of falling, the ball had accumulated a much larger downward velocity. After all, it's accelerating downward rapidly at the acceleration due to gravity. So, there near the bottom of the fall, the ball had a large downward velocity, and so its position was shifting downward rapidly. To help you observe the motion I just described, I need to slow the video down. So here's the same fall again at 1/10 of normal speed, slow motion, and I'm going to mark out the ball's position every 1/5 of a second. So 5 times a second, I'm going to draw a line to indicate where the ball is. Let's choose as the zero of position the point from which I dropped the bowling ball. That's 0. I can then measure the ball's position every 1/5 of a second and indicate it on the video. I can also measure the ball's velocity every 1/5 of a second and indicate it as well. But to do that, to make the measurement of velocity, I have to compare two positions at different times. After all, velocity is the rate at which position is changing with time. I need to look at the change in position to observe velocity. So here is the same fall, once again in slow motion at 1/10 of full normal speed, with approximate values for the ball's position and its velocity indicated every 1/5 of a second. As you can see, the falling bowling ball's velocity is increasing in the downward direction by about 2 meters per second every 1/5 of a second. It's a steady increase in the downward direction, so this corresponds to a steady acceleration downward. Over the course of an entire second, the bowling ball's velocity increases by about 10 meters per second in the downward direction. That's an acceleration of 10 meters per second, or equivalently about 10 meters per second squared in the downward direction. That's not a coincidence. This is a falling ball, and falling balls accelerate downward at about 10 meters per second squared, the acceleration due to gravity. So, this is a falling ball. Its velocity is increasing steadily in the downward direction at a rate of 10 meters per second, or 9.8 meters per second, if you like. Physics works. Well, you may find it helpful if I graph that falling bowling ball's position and velocity, each as a function of time. So here in this next version of the same video, I will give you a plot of the bowling ball's velocity versus time and the bowling ball's position versus time. Here we go again, slow motion, 1/10 of normal speed, the bowling ball falling out of the window. The ball's steadily increasing downward velocity is the hallmark of constant downward acceleration. After all, this is a falling ball, and falling balls are always accelerating downward at the acceleration due to gravity. That steady downward increase in the ball's velocity causes the graph of the ball's position to arc downward. For some thoughts on the shape of that arc, let's return to my laboratory. The bowling ball survived its fall just fine, but the ground outside the physics building has a pretty good dent in it. So, where do these motion curves come from? That is, for a falling ball dropped from rest, its velocity, plotted versus time, gives you a straight line. And its position, plotted versus time, gives you a curve that bends downward. Where does that come from? To answer those questions, we need to look at how the falling ball dropped from rest, how its acceleration depends on time, how its velocity depends on time, and lastly, how its position depends on time. The first of those, how the falling balls drop from rest's acceleration depends on time, is simple. It's a falling ball. Its acceleration is constant. It's the acceleration due to gravity, approximately 10 meters per second squared straight down. And we represent that by the little letter g. So, the falling ball's acceleration is just equal to little g, nothing else. Time is out of the picture. Second issue, the velocity of that falling ball dropped from rest as a function of time. Well, now time does matter because the falling ball's velocity starts at 0, but because it's accelerating downward, the velocity gradually accumulates more and more downward aspect to it. It goes faster and faster. After 1 second, the falling ball dropped from rest is heading downward at 10 meters per second, approximately. After 2 seconds, it's at 20 meters per second, approximately, and so on. All right? What's the formulaic relationship then between the velocity and the time? It turns out the velocity of the falling ball dropped from rest is simply the acceleration, which is little g, times time. Nothing else. So, that is the formula for a straight line. When you plot the falling ball drop from rest velocity versus time, there, get a straight line. The slope of that line is little g, the acceleration due to gravity. All right? That brings us to position. The falling ball dropped from rest's position is more complicated because to determine how far the ball has moved from where we started, we have to know the average velocity of the ball over the time we're considering, from start, from the drop moment to now, and we have to know its average velocity over that period, and we also have to know the length of that period because the ball will move using its average velocity to make progress, to go somewhere, to change its position. And the new position of the ball will be its average velocity times the time over which it's used that average velocity, namely the time between the drop and now, the moment in question. That that begs a new question, okay? So what's the average velocity of this ball dropped from rest? In many cases in physics, calculating that average velocity is difficult. This is a special, simple case where you can do it pretty easily. The average velocity of a ball that's dropped from rest is simply the average of its starting velocity times 0 and its ending velocity, the moment in question. Just take those two values and average them, because there'll be times early on when the ball was traveling more like the starting velocity, and there'll be times later on when the ball is traveling more like the final velocity, and that all averages out. The middle point in terms of velocity is the average. And so we know what the velocity of a falling ball is as a function of time. It's g times time. So the velocity at the start of the drop is 0. The velocity at the end of the drop is g times time, or not necessarily the end of the drop, but the moment in question, the moment we're paying attention to. So the average of 0 and g times time is g times time over 2, halfway between the two. So that is the average velocity of a falling ball dropped from rest. G times time over 2. The falling ball uses that average velocity to make progress, and it has amount of time to work with. So if we multiply g times time over 2, the average velocity, times time, we get the new position of the falling ball dropped from rest. It's g times time squared over 2. And that is the formulaic relationship between the position of this falling ball dropped from rest and the time it's had to fall. So there's the whole story. The relationship between acceleration and time is simple. It's a constant. The relationship between the falling ball's velocity and time is a straight line. It is the falling ball's velocity is proportional to time. G times time. And finally, the falling ball dropped from rest's position is proportional to time squared. It's g over 2 times time squared. And that kind of a formulaic relationship between position and time gives you an arc if you plot it against time. Time squared, if you plot time squared or anything proportional to time squared against time, it gives you an arc. And the shape of that arc is parabolic. So this is, the mathematicians would identify that and go, oh, that's a special kind of arc. It's a parabola, and parabolas show up all the time in falling objects, and we'll see more of them later on in this episode. During the first second of its fall, the stone is moving downward relatively slowly on average, and so it doesn't travel very far from your hand. But during the second of its fall, the stone is moving downward much faster on average, and so it covers far more distance during that second than during the first second. That's why, after only 1 second of falling, the stone is much closer to your hand than it is to the water. So we've seen that when you drop a ball from rest, all of its motion occurs along that vertical coordinate direction. And that motion is relatively simple. The ball's acceleration is that of a falling object. It accelerates downward at the acceleration due to gravity. The ball's velocity is also pretty simple. It starts at 0, because we're dropping it from rest, and then it increases in the downward direction in proportion to the time over which the ball has been falling. Lastly, that brings us to position. The ball's position we can define as starting at 0, and then that position increases in the downward direction in proportion to the time it's been falling squared. That's because as the ball moves faster and faster, it covers more and more distance with each passing second. So its velocity increases in proportion to time. Its position increases in proportion to time squared. Well, this is the simplest case of falling from rest. In the next video, we'll take a look at what happens if you have a ball that's not falling from rest. It's actually falling from a start in the upward direction.